Should I do it? Would it be better if I just did it? See, but do you think you'll get the answer? Okay. I feel like I should do it. What do you think, Matt and Amanda?
I just need it. Because I miss it. I miss this.
Could always watch the video. Could watch the video. Okay, no, Siva made a very angry face, so that means it didn't work out for you, huh? Let's have a look at it. Siva, do you mind reading the info to me?
A column of air contained in a vertical glass tube, partly filled with water and open at the top end, is made to vibrate at its fundamental frequency of 256 Hz. This happens when the length of the column is 0.310 meter.
0.310. Okay.
The velocity of sound in air is 340 meters per second. A, show that the end correction of the air column is approximately 0.022.
0.022, that's what we should get. Okay, so if you look here, if it's the fundamental, you probably want to see what I'm writing, huh? Yeah. Anybody watch the Super Bowl last night?
Only the trailers.
Okay, you didn't watch it live then?
No.
You know the Super Bowl? No. American football game. Yeah. Okay, so if it's the fundamental, how much of the wave fits in? There has to be a node here and an antinode here. So that's a quarter. The wave fits in. So if you were to use this formula, the wavelength, now let's just call this guy here L, which we know, and that's the frequency, and that's the velocity. The wavelength should equal 4L, right? Should equal that, except, as we discussed, there's a small problem, there's a bit of an error in calculating this. It's, if you remember the question we did last time, it's like a tiny little error of like 1 millimeter or something. What was it that they said it should be, Siva? Like 0.0 or 0.00?
0.022.
Okay, that's actually pretty big. Okay, so we also have the formula V equals F lambda. So let me change this into V over F equals 4 lambda plus error. Now what do we know? Do we know the V? Yes. Do we know the F? Yes. And do we know the L? Yeah. So the error is, let's see, 340 over 256 minus 4 times 0.31. That's equal to the error. So what do you get here?
0.022.
Do you really get it, or are you just reading? Because
I got it.
oh, good. Okay.
And that's 0.088.
That's quite different. is that that my handwriting's bad, is that 340 over 256 minus 4 times 0.31? Matt just told me you got 0.022. What did you get, Kim?
2.1.
Ah, come on, guys. You can't all have different answers now. Come on. Hang on. I know what I'll do. Prove you all wrong. 340 over 256 minus 4 times 0.31. Okay, good job, Siva. You are right then. It's 0.088. No, we're not quite finished yet. Yeah? That's okay. That's okay. Now, the reason that answer is a little bit different is because that's the error that you would have in calculating the wavelength. But I think they used the expression end correction, didn't they? Isn't that what they said? Yeah. So they want to know how much should you change the length by to fix the wavelength. So how much is this off by? It's off by this much. Error is this. Now, because you multiply the length by 4, you can correct, if you use 0.088 divided by 4. You know, like if this is a little piece that you add on which you don't want. So if you don't want that, the length has to be reduced. But you don't reduce the length by 0.088 because that would be too big because you're multiplying it by 4. You know, in my head I'm thinking about like this: 4L plus or minus, so in this case it's minus some correction plus the error. So because this guy is 0.088, then this one here has to be 0.022 then, because you're multiplying it by the 4. Yeah? Now that's okay. That is a hard one. I'm not surprised that you had trouble with that. And it's only something stupid like 2 marks, is it? Which kind of sucks. Yeah. Now the other way you could have done it. Can you still see if I zoom out? The other way you could have done it is you could have said wavelength equals 4 times the length plus some correction, and then don't have any error at the end. So you imagine that you figured out what the correct correction is. So here, if you were to do it this way, you would get V over F equals 4L plus delta L with no error at the end. And if you solve that, you would get out 0.022 if you put in all your numbers and solve this. So, I don't know which one makes more sense to you, which is more natural. But either way, it's not easy. So that is a hard one. What's the next part in it, Andek?
Water in the lower part of the tube is allowed to drain out so that the length of the air column is gradually increased.
Mm-hmm.
This continues until the air once again vibrates at its fundamental frequency. Determine the new length of the air column when this occurs.
Is it they said the same frequency or new frequency? Can I scroll down? So if you can just read that to me again, and let's just write down our info. So the V is still the same. Okay, fine. Go ahead.
Should I do the whole thing?
Yeah, might as well.
Water in the lower part of the tube is allowed to drain out so that the length of the air column is gradually increased. This continues until the air once again vibrates at its fundamental frequency.
Now, are they saying the same frequency? They said once again as fundamental frequency.
And determine the new length of the air column when this occurs.
I think it's the same.
Yes.
But that doesn't make sense, because if it's the same frequency, we'll get the same answer. Because they used the word fundamental again, didn't they? See, I'm not so sure about this because if I did everything again, if I have 1/4 here, then I should get the same answer. Do you know? Let's see. So don't write it down just yet. V equals F lambda. Maybe I don't get the same one. Let's see. So what's the lambda here, please? Okay, so what would be the length of the column here? It should be 1/4 of it, yeah. So what is 1/4 of this then, Matt?
0.332.
Is that not the answer from the first part? The length, was that not the length of the first part?
0.31.
Yeah, well we have to, don't forget we have to take away the correction. So what's 0.332 minus 0.022?
0.310.
Yeah, it's the same.
Yeah, so that's what my point was. I don't think it can be the same frequency. I think they meant something else. They either meant two things, and I don't know which it is. They either meant the frequency is different and it's still a fundamental, or the frequency is same but now it's on to the next harmonic.
I
So-
think they said it's a fundamental.
Yeah, but they said it's a fundamental?
Yeah.
Okay. But they also said it's the same frequency?
This continues until the air once again vibrates at its fundamental frequency.
Okay, I think it's a different frequency, but it's still the fundamental one, but it's different. Let's see. Do we have enough information to solve this now? V equals F lambda. No, we don't.
Do I check the marks?
I know, let's try and be good and let's try and figure it out first. It's better for our education this way. Siba, can you read it to me? Maybe if I hear it in a different voice, it will give me some ideas.
Water in the lower part of the tube is allowed to drain out so that the length of the air column is gradually increased. This continues until the air once again vibrates at its fundamental frequency. Determine the new length of the air column when this
I wish they were clearer. Okay, so we still think it's this. The L is definitely different.
I think it's open on both ends now.
Those sneaky pigs. Did you look at the marking scheme or did you figure it out yourself?
Because it says in the question that
No,
partly
she's-
filled with water and open at the top end, and it says in the part 2, water in the lower part of the tube is allowed to drain out.
Yeah. Oh, what sneaky pigs. So it's open at both ends now because they've opened the bottom to let the water out. Oh my goodness. Thank you, Siba. Well done on figuring that out now. Your English is clearly better than mine. Okay. So it's open at both ends. It's still a fundamental, but it's a different wave because what do you need here? You need antinodes. So this is an antinode. Yeah, okay, so it looks like this now. So how much of the wave is inside? Half a wave, isn't it? Yeah. And the frequency is the same. What was the frequency we got? 256. 256 hertz. Okay, so now let's see. V equals lambda F. So what was the lambda? I think it's the same, 1.3 something, wasn't it?
1.28.
This is 1.28, is it?
No, 1.328.
1.328. Okay, now what's the length this time? What's the length this time? See, it's not 4 of these. It's half of it, yeah. And don't forget, you still have to put the correction on.
Zero point six four two.
0.642 meters.
So what you half?
Hmm?
What you half?
The wavelength.
Oh, this is half a wave. Isn't it?
Yeah, when
Yeah.
both ends open.
Yeah. Half a wave fits in. Yeah. How many marks for that? 2 as well.
Yeah.
No likey. No likey. So how come you didn't get this right if you figured it out?
Figured that just now.
Okay. Well, this is why we're practicing together. Okay, so that's section A. Andek, if you slide through section B, do you see a wave question? There should be one of them.
Question 8.
Oh, no, A10 is a wave that comes up in atoms, which we haven't done yet, I think. So what about in section B?
Does this count? B4. B4.
What's the start of it? Read the first sentence.
A narrow beam of purple light contains 2 colors, red light of wavelength 6 times 60.
Okay, this is sounding like it. Is this a Young's double slit? Is there going to be a slit and an angle and...
Yeah.
Diffraction.
Yeah, yeah, okay.
Kind of.
Yeah, right. Let's try this one. Do you want to do it all together or bit by bit? What would you like? So, Kim, Siba, would you like to do it all and get all the answer or part by part? Part by part, okay. So how many marks for the first part?
2.
2. Okay, so that should take you about 2 minutes. So once you have it finished, let me know and we can have a look at it. You're looking confused, guys. Is okay or not okay?
Still working.
Violet is purple, correct, chat. You okay, Ken? You look a little bit sick. Are you feeling sick? Just sleepy, okay. How come you missed the last class? Were you asleep or sick? Yeah, okay. should be finishing the first one for 2 marks. Matt, got it finished or?
Nearly, I think.
Sibala? No. Stuck? Andak and Ken?
Maybe on it. But maybe I need help. So.
Okie dokie. Making progress, Siba? Yeah? I'm not sure how to understand your reactions. I see you rubbing out a lot, Matt, so maybe I should do it now?
Just one second.
Okay. Yes? I think it's time to do it. Siba, can you read it to me, please?
A narrow beam of purple light contains 2 colors. Red light of wavelength 6.00 times 10 to the power minus 7.
Is that red?
Yeah.
You said red, yeah. And then
And violet light of an unknown wavelength.
I'll call it purple. What the heck is violet? Right, lambda wavelength, okay?
The same light source is used in 3 separate experiments as described below.
Mm-hmm.
A. The narrow beam of purple light is incident normally on a plane diffraction grating.
Mm-hmm. Mm-hmm.
Determine the spacing between the lines on the grating if the second order red line has a diffraction angle of 4 to 7.
Okay, that looks okay to me. So the formula is n lambda equals d sine theta, and they're looking for the lambda. So lambda is d sine theta over n. Oh, sorry, what am I saying? They're looking, is this for the purple or the red?
It's like purple light contain red and violet.
Oh, purple is the mixture. So you have violet light and you have red light, and together they look like the colour purple is what they're saying, is it?
Yeah.
Okay. So, what? Oh, and it's mixed together. Yeah. So, I'm sorry, Siba, or well, maybe I'll get Kim to read it. Can you read it again to me?
It says an Arabic purple light contains 2 colors.
Yeah.
So, oh, okay, then.
Yeah, so the purple light contains red and violet.
Yeah.
Okay, and then you shine this light through a diffraction grating, yeah? And they give you the angle and they give you the order. Yeah? And what else do they give you, or what else do they say?
Incident normally.
Yeah, okay, yeah. But just be clear, which colour? Are they using purple, red or violet in this one?
Purple light.
The purple light. And what do they want? The D?
The lines.
The spacing.
The D then. Right, so, I think we have to use the other formula, perhaps. I don't know. What was the other formula? S equals lambda d over d. So let's just recap what we know. Do we know sine theta? Yes. Do we know d? No. Do we know lambda? Yeah, but we don't know the wavelength of the purple. Yeah. Now, it might not affect the answer much because these will be quite similar. So I'll just put a red circle, red around it. We know the N and we don't know the D. And we don't know the D. Oh, we don't know this one either. We don't know how far away it is from the screen. We don't know this. We don't really know this. We actually don't know this. Right, so we really have to use this formula. So we have D equals N lambda over sine theta. That's 2 lambda over sine 47.
9.71 times 10 to the minus 8.
What did you use for lambda? The 6? Now, hang on, pause, hit the pause button. Whoever wrote this exam was being very careful with their English, as we saw in the last question. Okay? So, Matt, can you just read the question part to me again?
The narrow beam of purple light is incident normally on a plane diffraction grating.
Okay, so far?
Determine the spacing between the lines on the grating if the second order red line has a diffraction angle of 47 red line.
Okay, I don't see how else I can do it other than by using this number here, though I'm not very happy about it. So what do you get when you use that?
1.64 times 10 to the power 96.
1.64 micrometers. That should, oh, that will affect the answer.
See, but how do you make your screen last longer?
Open the setting.
Sorry.
And Kim, do you mind checking the answer while they're messing with their phones? You check the answer, and it is this? Okay.
Display and brightness.
Yeah, ultra. Because you are on your this mode.
Low battery.
Yeah, no actually. Yeah.
Not auto lock.
Now,
You know this level.
Oh yeah.
just so you're clear, guys, I'm not too happy with this. The reason it works is there's 2 reasons why this works. Number 1, because red and purple are similar wavelength. No, are they similar?
So the
Or
question
red and violet. Yeah.
The question says if the second order red line.
Now there you go. That was the key. Okay, so yeah, you need to emphasize it's at the second order red. Yes, so we could use the red wavelength. Yeah, okay, that makes me feel better now. Okay, I feel better now, right, so that's fine. Did they underline the word red or? No, okay. Okay. You guys need to learn what words to emphasize when you're reading, so. Okay, next part. What are they asking in the next part, Siva?
The third order violet line is also at this same diffraction angle. Determine the wavelength of the violet light.
Good, good. Okay, so what they're saying is the angle for order 3 for violet is the same angle as 47 degrees. I think you can figure out the lambda for this one. You have that done already, Kim? Great. You got it right? Perfect. And how many marks is it? That's okay. I think everybody's getting this. So the D is 1.64 times 10 to the minus 6. the sine is of sine 47 and the n is 3. So what answer do you get this time?
3.99 times 10 to the power of -7.
Does it round up or is it 3.99?
3.998.
So it would round up to 4 then. So that would be 4 times 10 to the -7. So that's 400 nanometers then for the violet colour. Okay, and what's the next part? What do they ask you to do?
The purple light is then used in a lamp in a Young's double-slit experiment. The slit spacing is 0.25 millimeters, and the distance between the fourth red fringe on one side of the center to the other fourth red fringe on the other side of the center is 24 millimeters. Determine the distance between the double slits and the screen.
Good, so that's determined the big D. Okay. I think, how many marks?
3.
3?
This one's 3.
Yeah. Okay, give that one a try, guys. I think you can do that one. And remember, what colour is it? Violet this time, is it?
Ray fringe.
Red this time. Red? Okay. Got an answer, Matt? Yeah. Siva? Kim? Okay. And what did they say the distance between the fourth and -4 on the screen? 25 millimeters, you said? 24 millimeters, okay. And did they give you other information? Did they give you the D, the slit?
The slit spacing and the distance between the fourth red fringe on one side. Wait, no, sorry. The slit spacing is 0.25.
0.25 what? Millimeters?
Yeah.
Okay, let's have a look here. So, they tell you in the question, here to here is 24 millimeters. That's 8 fringes. Okay? So that means S is 3 millimeters. The distance between them is 3. Yeah? Now you have the formula S equals lambda D over D. Yeah? So that means 3 millimeters equals 600 nanometers times big D, which is what we want, over small d, which is 0.25 times 10 to the minus 3. So I can get the d here. The d will be 3 times 10 to the minus 3 times 0.25 times 10 to the minus 3 over 600 times 10 to the minus 9. So that should work out to be a reasonably sized number. Problem? Is red. This, goodness, I hope so, because Matt told me it was red. Is it red? They say red fringe?
Yeah.
Yep. Right, so what answer do we get here?
1.25.
So what confused you here, Siva? What went wrong?
I chose the purple.
Oh, well, yes, okay. That would be a problem for sure. And Ken?
I didn't understand the question.
Okie dokie. Can you read the next part, please, Ken? What's the next question?
Determine the spacing between the violet fringes.
Oh, okay, yeah. So, what's that, like 2 marks, 1 mark? 2 marks. So they want you to use this formula here, but this time for the other light. So do you know the wavelength of the violet? You do. Do you know the distance to the screen? Now you do. And do you know this slit separation? You do. So you just can calculate it by multiplying.
Zero
0.002 meters. Yeah. So 2 millimeters? So, Mark, what was the formula? What was the wavelength of the other light?
4 times 10 to the power 87.
And then the small d was 0.25, wasn't it?
Times 10 to the power 23.
Yeah, and you said this comes out as 2 millimeters. Okay, that's fine. What's the next part there, Matt?
Sorry. Finally, the beam of purple light in air is incident on a triangular equilateral prism
No.
at an angle of 55 degrees to the normal at face AB.
Okay, hold on. Right, so do they have a picture?
Yes.
Is it coming in like here or here, top or bottom?
Bottom
Okay, so it comes in an angle of
55.
55 degrees, and this is air, and this is, of course, glass or something. And they must give you a refractive index, do they?
Yeah. Determine the angle that the red light makes with the normal as it leaves the prism at face BC. The refractive index of the prism for red light is 1.513.
1.513.
513 for red light.
Okay. So, It goes along here, then it hits here, and then it exits again. So I kind of have my, I'll try and draw a little bit nearer.
It goes up.
In the picture they were going up,
Yeah.
thank you, that will help me. So like, what, like this?
Slightly up, like this, like slowly.
So it does, it goes like, would you say, like that?
No.
When in
Less.
lower, it's like straight line up 1 degree.
So
Yeah.
it goes
A little up.
a little up from that. Okay, thank you. And then what happens?
A little down.
But nearly horizontal,
It's just
No.
like
Yeah.
this.
no
Slightly
down,
low.
slightly.
Yeah.
Yeah.
Okay, fine, thank you. Right. Okay, let's fill in some angles, right? So that's 55. That's 60. That's 60. And that's 60. Now this angle here, we can get this one because we can use our formula sine theta 1 over sine theta 2 equals n1 over n2. So this can give us our theta 2 here. The oh sorry, that's the wrong one. Sorry, it's with the normal. So that's it can give us this one. Yeah? This line I did is the normal. So you measure the angle with the normal. Question, Siba? You're looking a bit confused. Are you sure? Is that okay? Like this? Yeah? So let's see. Theta 2 would be sine inverse. Sine inverse 1.513 sine 55, I guess. Bring that up, bring that up. Yeah. So what does that work out as?
I get there.
Yeah, because I have this upside down like a fool. Sorry. That's 1.513 on the top and 1 on the bottom. So that means here the 1.513 should be on the bottom, not on the top.
$32.8.
32.8 degrees. Okay. So look, if that's 32.8, then what's this angle, which will be 90 minus 32? So that's 57.2, is it? Now, if these three add up to 180, then this angle here, I'll just squish it in, that should be 62.8, I think. Yeah. Now, if this angle adds up to 90, then this angle here, the one we really care about, that would be something. 27.2. And that's the angle I care about because that's with the normal. And then we want to get this angle here, which is theta 2 again. So you have sine theta 1 over sine theta 2 equals n2 over n1. So theta 2, hang on, let's see, that over n2, which is 1 over n1, yeah. Oh, is this going to work or is it going to be another error? Sine inverse 1.513 sine 27.2. Let's see what that is. And this is our answer. $43.8 for 6 marks, we hope. Is that the answer for 6 marks? And that's the end of the section B question, is it? There's another part?
No, there's one, but it's not waves. So.
Oh, it's not waves?
Yeah. There's some.
Is it 43? Make me happy and tell me it's 43.8. Wonderful. Wonderful. I don't know. 6 marks? What you think? Don't worry, Steve, it's recorded. What do we think? Good or bad? Not very bad, okay. There's no more waves in that exam?
No.
No? Let's have a look at version 2. So, section A wave question might be around about 7, 8, 9 or 10. No battery?
Yeah. Huge power.
Yes, indeed. Can you charge your power bank up from that?
Is it iPhone?
Hmm?
Is it iPhone?
Yeah.
You could put your power bank in the middle and charge everybody up.
Can I? Does it fit? Yeah, that's right. Thank you.
Oh, I thought you needed yours charged up, Kim. You have enough battery power?
Mine?
Yeah.
You have your battery?
Yeah.
You have enough power?
100.
Oh, 100%. Nice, okay. Right, what's the first wave question in version 2, so? Is it A6? Now, sometimes the wave question actually isn't a wave question if it comes up later.
No.
Well, read it to me and I'll tell you.
A diamond is placed in a tank of water.
Yeah.
Determine the critical angle for ray of.
That's a wave question. And that's a tough one. So, well, it's not so bad. It's a diamond placed in water and they want the critical angle, yeah? And they give you the refractive index of the water and the diamond? Yeah. Okay. 1 mark, 2 marks?
2 marks.
2 marks. Okay, you should have the first part done. Is there a second part? There is a second part. Antek, is there a part 2?
Yeah.
Yeah. Got it finished, Matt? Finished?
Part 2.
How many marks is part 2? Yeah. Continue. Shall I do this one now? Yeah, Matt, Siba, and Kim. Ready? Okay. So, what's the refractive index, Siba, for the water and the diamond?
For diamond is 2.417,
Okay,
and for water is 1.330.
2.417 and 1.33. Yeah, so what critical angle do you get here?
33.4.
Okay, fine and dandy. So what's the next part?
Determine the wavelength of the sodium light in the diamond if its wavelength in air is 589.3.
Okay, so you have air and you have diamond. And the air's refractive index would say is 1. And the diamond's is 2.417?
Yeah.
Yeah, okay. And the wavelength comes in, and then it refracts. It diffracts. Refracts. What's the wavelength? Did they give you the wavelength in air, is it?
Yeah, it's 589.3.
Nanometers?
Yeah.
Okay. So look, this one here is where it's useful to use the other formula for Snell. So look, you have sine theta 1 over sine theta 2. That's equal to lambda 1 over lambda 2. But don't forget you have sine theta 1 over sine theta 2. You still have the first formula, which is n2 over n1. So by combining the two formulas, you can get n2 over n1 equals lambda 1 over lambda 2. So lambda 2 would be n1 over n2 lambda 1. So your answer is 1 over 2.417 times 589.3 nanometers. So what's that? That was kind of a sneaky one. Nanometers. Did anybody get that? Matt, what happened for you?
Oh, I used the water index
Ah, yeah.
because the diamond is inside the water and the water is.
No, fair enough. Fair enough, yeah. I don't think that's what they meant, though. I hope not, anyways. Because then it's harder. Is that the right answer? That's right? Yeah. Yeah? Yeah, great, okay. I don't think there's any more waves in section A, so let's have a look at the section B then.
Is it
Oh, there's another wave one?
yeah.
And what's it about?
Mercury light is incident normally on
Okay.
diffraction rating.
Alright, okay. That's strange that they have two. So, how many marks for that one, that question?
3.
Any parts?
No, just 1.
Okay, give that one a try. Let's make a note. are we ready for the next part? Yes? Or do you need another minute? Ready? You got it finished? Oh, can't do it? Can you read it, Siva?
Mercury light is incident normally on a diffraction grating. The third order spectral line of this yellow light of wavelength, 577 nanometer, has a diffraction angle of 78 degrees. Determine the diffraction angle of the second order green line of wavelength 546 nanometer.
546 nanometers. So this question's a bit sneaky, well, a little sneaky, because it comes in two parts. So part one, you first have to figure out what the diffraction grating is. And you can do that using the formula. You know the formula n lambda equals d sine theta. So, you know, if you have the formula n lambda equals d sine theta, then d is n lambda over sine theta. Like that. So we know n, don't we? And we know lambda, and we know theta. So we can get the d. And then what we can do is we can feed that into the next part. What order did they ask for? The third order again? The second order. They want the angle, is it? So whatever answer you get here, you can feed that into the next part here. And then you can get the theta. So you can say theta is sine inverse, if I use theta is sine inverse n lambda over d. Okay, so let's do the first part here, Matt, if you have this. What is 3 times 577 nanometers over sine 78?
1.77 times 10 to the power -6.
So micrometers then. And then if you put that in here for the next part, we can work out the angle for the second order. It'll be sine inverse 2 times 546 nanometers over 1.77 micrometers. And that gives us the answer we need.
38.1.
Okay. Yeah, that was kind of a bit more unusual. What threw you here, Siva? What threw you on this question? You know this expression? Like what caught you out?
I didn't understand the question.
Kim, do you have any success with this question? Good job. Okay. And you didn't want to help Siva. That's okay. I'd do the same thing in your situation. Okay, is there any more waves in section A? No. Section B? Not ones with word function, yeah. There's no waves in section B?
No, I think it. No.
So they gave you an extra one in section A instead. Okay. Was that version 2?
Yeah.
Right, let's have a look at version 3. But let's see what's in section A first. See if there's anything weird in version 3. You guys are so low on energy, you're making me feel tired. Were you in class at 9? You were, you had maths at 9. Yeah. Ah! You were up late finishing your coursework. Right? Yeah, it all makes sense now. Well, I was up late watching the Super Bowl, so that's why I'm tired. Okay,
A8.
A8, read it to me, and what's the story?
Sodium yellow light contains lines of wavelength 580 nanometers and 586 nanometers. A narrow collimated beam of this light is incident normally on a diffraction grating having 500 lines millimeter
Per millimeter, yeah. And what did he ask you to figure out?
Determine the highest refracted order observable in the transmitted light. And for this highest order, calculate the angle between the two diffracted yellow lines.
And there's 2 lights, there's 2 wavelengths, is there?
Yeah.
Yeah, yeah,
580 and 586.
yeah. So, what's going to happen here is one of the colours will be spread out, and then the other colour will be spread out as well. One of them will spread out a little bit more than the other one. They asked for the highest order, did they? So
Yeah.
you might as well give the highest order for both. Now, just to help you out here, just to remind you, you have the formula n lambda equals d sine theta, yes? And you remember we said n lambda over d equals sine theta. But sine theta must be less than 1. It can never equal 1, because then what happens if sine theta equals 1? What's the theta? 90. So it means the light actually never hits the screen because it moves parallel to it. Okay? So this means that n should be less than d over lambda. So by using this formula, you can get the maximum order for both lights. Do they provide you with the d? Oh, they do, but they do it kind of an unusual way. They say it's 500 lines per millimeter. So then to convert that, what do you do? No, you got it right last time we did this. If you have 500 lines per millimeter, how do you get the d?
Divide by.
That's it, yeah. Is 1 millimeter divided by 500 is the d. Okay? I think you can do this. Give it a try. Oh, Kim, you're making me so tired. What time did you finish your coursework at? 3 a.m. p.m.?
I slept like 11, 12,
Good for you. When did you wake up?
8.
So why so sleepy? Well, what did the question ask precisely? What did they say?
Determine the highest diffracted order observable in the transmitted light.
You see, it's possible, see, but that it'll be the same number for both, and this is perhaps why they don't specify. Are the wavelengths quite similar?
580 and 586.
Yeah, so it's probably the same number. Did you get the first part?
No.
What did you get, Siva, for your first answer? Yeah?
3412.96.
For N? I don't know that, Siva. What do you have on the top? What's your D?
2 times 10 to the power minus 3.
Okay. Are you sure? That doesn't seem right. For the D.
1 over.
It's 1 millimeter. Millimeter is 10 to the minus 3. Matt, what did you get here for the D?
3.45.
10 to the minus.
Oh, sorry. D.
What did you get, Siva?
2 times 10 to the power negative 6.
Yeah? What? Is that?
Wait, it's 1 divided by 500.
No, it's 10 to the minus 3 divided by 500.
2 times 10 to the power minus 6.
Yeah, that's right. Okay. So when you put the D over the wavelength, what do you get? You're making this a lot harder than it is. What do you get?
3.41 times 10 to the power minus 9.
Oh no, Siva. No.
3.45.
Okay, that sounds right. I think you have something wrong.
No, I didn't put the.
Nano.
Yeah.
Okay. And for the other wavelength, what do you get? So in both cases, the maximum order is 3. Okay? You made a, what's the expression in the English? You made a dog's dinner of that. You made it much harder than it needs to be. Do you know that expression? So this is when you like take beautiful food and you work on it, and then it gets worse, and then you have something only good enough for a dog. So, good job. Okay, right, I better do the next part. Siba, do you mind reading the next part? What happens?
For the highest order,
Yeah.
calculate the angle between the 2 diffracted yellow lines.
Oh, okay, that's okay. So the highest order is 3. So you have n lambda. So what's one of the wavelengths then? Can you give me one of the wavelengths, Kim? 580 is one of them, is it? Times 10 to the minus 9. That's equal to d sine theta. Okay? And then for the other one, what will happen is they're only different by a little bit. We want the difference here. So for the other one, it's 3. What's the other wavelength? 586 nano. That's also equal to 2 times 10 to the minus 6 sine theta. So you have two angles to calculate. The first one would be sine inverse 3 times 580 times 10 to the minus 9 over 2 times 10 to the minus 6. And then for the other one, the only difference is you change the 580 into 586. Everything else is the same. So I'll just put dot 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 586 dot dot dot. Okay, so what are the two angles here then?
60.5.
Okay, so the first one is what?
60.5.
And the second one?
61.5.
Oh, so they differ by, the difference between those two angles is 1 degree. How many marks for that part?
3.
Okay. Okay, got that? Is that one okay? Is there another section A wave? No. Section B?
Yes.
Okay, what's that one about?
It's basically definitions.
Right, well let's do the definitions together. So what's the first definition they ask you for, Andek?
Amplitude.
Amplitude. Siba, what's amplitude for a wave? What's the definition? Correct. You don't sound sure, but that's right. Okay, good. Matt, what's the next definition?
Wavelength.
Kim, what's wavelength? Yeah. Now, remember in the exam you can't write this down, so you have to use a sentence. So, what would we say? Ah, yeah, well, if she can't get it, we'll give you a go. What do you think, Kim? Yeah, but could you give me a verb and a sentence? So, it's a what, say again? You go on. Between. Okay. Yeah, so just in the exam, remember to write a full sentence. So the wavelength is the distance between two neighbouring crests in a wave. That's fine. Or between two neighbouring troughs. Yeah. Is there more definitions?
Frequency.
Okay, Matt, what's frequency? Yeah.
Time taken for
No. Try again.
1
Oh. No. That's true, but give me a sentence. Andek, do you think you know? You can put in a sentence?
Each time a wavelength passes by.
Not too bad, but not going to do it, I'm afraid. Siba? Frequency? Go on. That's it. Number of cycles completed in a second. And a cycle could be a wave, it could be a circle, whatever the context is. Is there more definitions?
constructive interference.
Okay, Kim. What's constructive interference? Oh no, don't look. Don't look. Or Siba, do you know?
1, 2 waves.
Mm-hmm.
Propagate,
Not propagate, not propagate, not oscillate,
vibrate,
not vibrate.
meet,
Meet, yes, and
maybe larger.
that's it. So a constructive interference is when two waves combine to form a wave of greater amplitude. More definitions?
Yeah.
Go for it. What's
Destructive interference.
Okay, and what's destructive interference?
It's when two is combined but just destroys each other.
Yeah, now doesn't it have to necessarily completely destroy each other? So you could just say when two waves combine and reduce the amplitude. Okay, more definitions?
No.
How many marks for all those definitions?
5.
Okay. Right, what's next now?
Briefly describe the Young's double-slit experiment.
Ah, wonderful. Siba will explain that to us. So Siba, briefly explain Young's double-slit experiment. That's the next one. Go on. I do. Are you writing the answers or the next question?
Yes.
Okay. So, Matt, Young's double-slit experiment. You need to think about the experiment Young did. Remember, he used the... It doesn't have to be this, but you use the light and you split it. Okay, so do you want to try and give me a sentence? No?
Like,
Okay, I'll help you guys out. So,
is it?
you go on.
Is you see on the paper?
Yeah, okay, yeah.
There's a paper with slit and there's a paper in the back.
Yeah, so, good. Okay, so we got the idea. So, Young's double-slit experiment, you have a single beam of light and you incident that or you shine that between two narrow slits, and then that is shone onto a screen. And then what do you notice on the screen?
Many different.
Yeah, most importantly, you get more than 2 dots. So although there's only 2 holes here, you do not get 2 lights on the screen, which you might think you should get. What do you get on the screen?
More than.
You get more than 2. This is called an interference pattern, and it shows that light is a wave. Yeah? So you need to put this into a sentence. You know, so I'm actually curious to what they say in the marking scheme. How many marks is that? 2. So maybe that's like, for me, 2 marks means 2 good sentences. 2 good sentences. Kim, can you read what they have in the marking scheme if you have it there? What do they say to write?
What if I say light passes through a paper with 2 slits and in result more than 2?
Yeah, that's okay. Let's see what the marking scheme says. Yeah.
Narrow beam of
Monochromatic.
light is passed through a narrow slit and is then incident on a double slit. That's for 1 mark.
Okay.
And the light leaving the double slit is coherent, and when it reaches a screen placed beyond the double slit, interference of the beam occurs, producing a fringe pattern.
Yeah. So they're saying the same thing, but just in different words. So I said the light has many points on the screen, and this is because it's an interference pattern because it's a wave. You know, it's the same thing. I think if you can try to put in your own words, you've got a better chance of remembering it. So how many marks do we have so far for this definitions now?
7.
7, alright. So do we have a calculation yet? What's the next one? And
Explain how this experiment
no,
confirms.
not yet, okay. Go on, what is it?
Explain how this experiment confirms the wave nature of light.
Good! So Siva, or Kim, how does this experiment confirm or show that light is a wave? What? Go on, Kim, what was that? No, tell me. What'd she say, Siva?
Is it that?
Okay, you could write that in the exam, but Matt, any ideas? So look, this is what I would say, okay? I just said it a moment ago. when you have the screen, okay, and you have the light and it comes in between two slits, you were expecting maybe to get two colours here just, okay? Imagine you had two slits and you fire like little marbles, little beads, okay? If you fire them between the two slits, some of the beads will go through one hole and some will go through the other hole. So some will hit here and some will hit here, okay? But that doesn't happen with light, because light is a wave and it produces some here, here and here. Why is that? Because some of the wave...
Disperses.
Yeah, well no, it's because of the constructive interference. So sometimes the wave combines to make a bigger wave, and sometimes it destroys and make no wave. So it's like an ocean wave coming in, and sometimes you get peaks, and then sometimes you get troughs. So in other words, because you get an interference pattern, this demonstrates that light must be a wave. Because you can only get an interference pattern with a wave. That's it. So, how many marks is it?
2.
2. So you would say, because an interference pattern is produced, it must mean light is a wave. Now, what did they say in the marking scheme, Kim, if you have it open?
Sorry, can you repeat the answer?
Well, that's just my words. Like, let's see what the marking scheme says. I said, Andek, I said, because you get an interference pattern, it must be because light's a wave. What's it say, Siva?
In order for the light from the double slits to interfere, it must be traveling as a wave motion, where the light rays arrive in phase, constructive interference occur, and where the light is out of phase, destructive interference.
Yeah, what I said, but more words. Yeah. Yeah. You can write theirs down, or you can use mine. Right, what's the next question, Andek?
In a Young's double-slit experiment, the double-slit spacing is 0.52 millimeters and the slits are...
Okay, so this is an actual calculation now.
Yeah.
So in a Young's double-slit experiment, what's the info?
The double-slit spacing is 0.52 millimeters,
Okay.
and the slits are placed 0.95 meters from the screen.
Okay.
Determine the fringe spacing when light of wavelength 630 nanometers is incident.
Okay, so what formula do we use here? They want the S. So what does the S equal? Lambda, which we know, D, which we know, and D, which we know. So let's not bother calculating that, because that's fine, right? What's the next part?
Yeah. Oh.
Yeah.
A ray of light in air is incident of at 35 degrees to the normal on phase.
What angle?
35.
35, okay. Yep.
To the normal on face AB of a triangular 60 degrees prism.
Oh, not the prism again. Is it the prism again?
Yeah.
So all that's different is this angle is 35, whereas in the other question was a, whatever, 52 or something.
And the refractive index is 1.5.
And blah, blah, blah. Is it 6 marks again?
It's...
No, it can't be 2, because that question's...
No, there's 3 questions, but
2 then 3
9
and 4.
Oh, they break it up, do they? Ah, so how do they break it up? What do they want? Oh, so did they help you by breaking it up into stages? So what's the first part?
Determine the angle of refraction at this face.
Yeah, so what they've decided to do here, and rather make it one question, they made it 3 questions. So the first thing was to get this angle, was it? Okay, and then what's the next part to get what?
Determine the angle at which the ray leaves the opposite rays AC of the prism.
So this angle?
Opposite face.
I thought you said there were 3 parts. So what's the third part?
The angle of incidence at the first face is then changed so that the ray just undergoes total internal reflection.
Ah, okay, so it's not related. It's a kind of a different question. So they say it's find the critical angle. Okay. Right, well that's the only part that's different to what we did a moment ago. But we have the formula for critical angle. So what did you say the refractive index for the prism was? 1 point?
5 1.
Right, so that's for the last part, that's the critical angle. But the other two parts are what we did earlier this afternoon. Yeah. I kind of want to give you a question for homework. What version was that? Version 3?
Yeah.
The last question, this is the formula.
For critical angle. Yeah. It's Siba, it's sine inverse n1 over n2. Right, what year was that? 16, 17?
Yeah.
Okay, so your homework 15, 16. I don't mind which versions you look at. I just want you to practice some. So I think it would be a good idea if you practiced. When's our next class? Is Wednesday? Not tomorrow, right? Yeah, what I think would be good for you to do
Yep.
I'll be a little nicer, sorry. 3 section A questions and a 1 section B question. Just as a little bit of practice, okay? It's not going to kill you, I promise. Huh? Yeah, just find, look, I think this one, maybe there's four versions. So just look at them, pick out 3 section A's to do and 1 section B. Okay? Don't just pick out the easiest section A's and section B's. Right? You need to start thinking now about the final exam. So you need to be doing some exam questions at home, okay? You need to be thinking about the fact that you have an exam in the summer and your future depends on it. No pressure. Do you have class at 3? You're finished?
Yes.
Oh, we could have kept going then for another 10 minutes, but okay. Oh, active listening tomorrow, huh?
Yeah.